So obviously I'm going to talk about totally unimodular matrices today in linear programming, just to give you an overview of just the basic stuff that I wanted to cover today. We're going to give definitions to unimodular matrices and totally unimodular matrices, give a couple properties about them. I'm going to state and prove one theorem about using totally unimodular matrices in linear programming, and then we're going to apply that to some graph algorithms, because a lot of standard graph algorithms can be characterized as a linear program with a totally unimodular constraint matrix. So that is what we're going to go through. So first of all, just a couple quick definitions. So square matrix, let's just call it U, is unimodular if its determinant is 1 or -1. So it's non-singular, it's got determinant 1 or -1. Now, a matrix, let's call it M, doesn't have to be square. It's totally unimodular if every non-singular square submatrix of this matrix M is unimodular. So choose a certain number of rows and choose that same number of columns. You've got yourself a square submatrix. If that square submatrix is non-singular, then it has determinant 1 or 0. And another way that we're going to characterize these, this is exactly equivalent to saying every square submatrix has determinant 0, 1, or -1. So if it has determinant 0, it's not non-singular. If it has determinant 1 or -1, then it's unimodular. So you can characterize totally unimodular matrix M in any of these two ways. Okay.
So, question.
Yeah.
That
question.
The submatrices of size 1?
Does that include submatrix size 1? Yes,
Okay,
actually.
So all the entries are either 0, 1, or -1?
And that was my first property that I'm going to get to next. So given these definitions, before we jump into a theorem, we can state a couple properties about these. So the first property is indeed that every single entry of a totally unimodular matrix is 1, 0, -1. So let's say if M is, I'm not going to write out totally unimodular every time, so let's just say TU from now on. Every entry of M is 0, 1, or -1. Okay, why? Because every 1 by 1 submatrix has to have determinant 0, 1, or -1. Also, if M is totally unimodular, there are a lot of matrices that are associated or related to M that are also totally unimodular. Among them, just -M or M transpose. These are both totally unimodular. And the last thing, which I'm going to give a quick step of the proof in showing, is that this matrix, where I take M and I tack onto it an identity matrix, is also totally unimodular. Okay. I'm not going to go through a whole proof of this, but let's just take a look at maybe the first step, illustrate the first step of a proof that if you take a totally unimodular matrix, tack on an identity matrix, it's still totally unimodular. So this is a proof step. This third thing that I mentioned, just the step is if E sub I is just a vector with a 1 in the ith position and zeros everywhere else. So it's a vector of all zeros except for a 1 in the ith position. Then let's just talk about why tagging that one vector onto M still produces a totally unimodular matrix. And if we can believe this, then we can believe this is true, because this is just tagging on a whole bunch of vectors like this one. So just for the sake of illustration as we're going through this, take a small, this happens to be a totally unimodular matrix. And if I tacked onto it this vector right here, just use this as an illustration as we go through the proof of why this whole thing now is going to be totally unimodular. So we choose a square submatrix U of this matrix here by selecting some integer k rows and k columns. Okay. And if I include the last column in the ith row. So what am I doing with including the last column in the ith row? Basically, I'm making sure that the submatrix has this 1 in there. So if when I choose my rows and columns, I include the last column and ith row, then the determinant of this thing that I end up with, well, for example, let's say I choose that submatrix right there, and so I'm trying to find the determinant of that 3 by 3 matrix right there. Well, we know how to take a determinant. I can choose one row or one column, and it's going to be an entry times a cofactor plus an entry times a cofactor. This 1 is the only non-zero entry, so this determinant is going to be plus or minus 1 times the determinant of some other matrix. We can call it M star, where M star is a submatrix of M. Okay, this is pretty much it. This is the main idea right here, just because if M star is a submatrix of M, it has determinant 0, 1, or -1. Multiply that by -1 or +1, I still get something that's plus or minus -1. Now, what happens if I didn't have this case where I didn't choose the last column or the ith row? Well, if I don't choose the ith row, I get a column of zeros in my submatrix. It has determinant 0. Or if I don't choose the last column, then all I'm doing is choosing a submatrix of M anyways. So of course it's going to have determinant 0 or 1 or -1. Okay. So not a full proof right there, just the idea behind how I can take a total unimodular matrix M, tack onto it one vector, or if I want to, eventually the whole identity matrix, and I'm still totally unimodular. Okay, let's talk about our main theorem that we're going to use later to apply to some graph algorithms. For this theorem, I want M, let's say it has dimensions M by N. I want it to be full row rank. By the way, I would like there to be more columns than rows. I want it to be full row rank. Of course, totally unimodular. Let's say that I have this vector B. It's length M and it's all integers. It's a length M integer vector. C is going to be just a coefficient vector for a linear program. It can be anything from the reals. Now, given all this, you can say then the linear program minimize C transpose times X. X is my unknowns that I'm solving for, subject to the constraints M times X equals B. And I want all of my X's to be non-negative. Then if I have this set up, this is just a standard form of a linear program. So how do I word this? Then the linear program has an integral optimal solution. Let's call it X star.
So what if B is not an integer?
If B is not an integer, this is not guaranteed to be true. And you'll see as we go through the proof at what point I'll be able to point to why I need this to be integral. So we'll see that. So I'm just saying that I can find some optimal solution, and this is all integers. Okay. So before we go into the proof, why is this significant? Well, normally, if you just had a linear objective function, you have a set of linear constraints, and then you restricted your answer to be integral, then in the general case, that's an NP-complete problem. It's integer linear programming. That's not near as easy as just linear programming, but what we're saying right here is if I have the right constraint matrix and the constraint vector, I don't have to explicitly require that x be integral. It's going to just end up automatically being integral. So that's the beauty of this theorem. That's why this is useful. That's why it's nice. So let's go through the proof of this. So just some standard stuff from a course like CS 520 or any course on linear programming or optimization. We know that a linear program like this, so this linear program, like any, has an optimal solution that's a basic feasible point. Or what do we mean by basic feasible point? And I'll define that in a second, but we also talk about these basic feasible points. These are just vertices of the polytope. Okay, you have your constraints matrix. It defines some geometric region, this polytope where I can get feasible solutions. And at the corners of that polytope, so if I've got some feasible solution, the corners are the basic feasible points. So a basic feasible point, i.e. a vertex of the feasible polytope. Okay. So the LP has an optimal solution that's a basic feasible point, and what we're going to show now is that every single basic feasible point is integral. So if every single basic feasible point is integral, then certainly we have an integral optimal solution. Okay. Claim every basic feasible point is integral. Okay. So that's going to be our next step. So what is the exact definition of a basic feasible point specifically for this? So a vector x is a basic feasible point if three things have to hold. First of all, it has to be feasible. Okay, but beyond that, we're also saying that this vector, whatever it is, it has at most m, which is the number of rows, non-zero entries. And when we choose those m entries that are the non-zero entries, then we're going to say they correspond to, we say they're given by script b of x is just a subset. Those integers is just the entries of the non-zero values in x. And the third thing that we need to make sure is true is the submatrix of the constraint matrix, M, formed by just taking the columns of those M non-zero entries, or those indices. So I'm taking the entries, the indices, I'll call them the indices. Let's call this submatrix A. It's non-singular.
Can you give an example for that?
Can I give an example? I have a matrix M, has more rows than columns, and I'm going to be multiplying this by a vector x, and I want to say that that's equal to b. Then what I want to do is I want to choose n, not n, I want to choose just m columns from here basically what I'm going to get to next is I'm going to be able to solve this, where x bar is just the non-zero entries of M. So I guess I don't know how I would show an example so much as you just take your matrix M and just choose M columns so that it's non-singular.
Isn't this similar to steps of the simplex method?
Yeah, so what the simplex method does is it bounces around on all the different basic
But you
feasible
have, like, the
solutions.
basis, you have to have a sub, like when you take your basic indices, they have to form a non-singular.
Right, they always have to form a non-singular matrix. Exactly.
They don't, you take another set.
Exactly, yeah. So I mean, if I were to grab M entries in here and I end up with a matrix that's not non-singular, then I can't do that. I wouldn't do that anyway. So in the way the simplex method does it says I'm going to choose M of these, make sure it's non-singular. If it's non-singular, then I have a basic feasible point.
So to clarify, is this step where we're using that full row rank assumption?
We're using, exactly, yes. We're using the full row rank assumption here. And later we can take a corollary and relax that a little bit. It doesn't need to be full row rank, but just for this version of proving it, we want it to be full row rank.
Yes.
I was going to say, it doesn't sound like we're using full row rank. We're just using totally unimodular because any subset, any square submatrix has to have a determinant of 1 or -1 and therefore is invertible. So any square...
Any square submatrix has to have determinant 0, 1, or -1.
Right.
Yeah.
So we are using full row rank.
Right, so-
At least one has to have.
That's my question. I mean, I see you using it implicitly in this proof, but
Right.
would the result really break down if you didn't have full row rank?
No, you wouldn't.
Okay.
I just prefer to say it's full row rank.
Yeah, the theorem is definitely true. But
Right. So given this theorem, the next thing I'm going to do is just give you a quick corollary and not go into details to show you why we can relax this. But for the sake of the proof right now, let's say we have a full row rank matrix, and we're going to take a look at just one basic feasible point. So anyways, this all kind of leads into what the next step was anyways. The fact that I have now this submatrix A of M. M was full row rank, A is non-singular. That means that I should be able to solve this system right here, where x bar is just, it's a subvector of x corresponding to those M entries. Corresponding to the entries, those indices from B of x, okay? Here's kind of the cool part. What are all of these entries of x bar? So I take just any old entry here of x bar. Kramer's rule states that one entry of this vector right here is the determinant of some matrix, we'll call it A sub I, divided by the determinant of A, where this is the matrix obtained by replacing the ith column with the vector B. Okay? So what does that mean for us? And Varun, this is where we're going to use the fact that B is integral. M is totally unimodular, so A is unimodular. So that means the determinant of A is plus or minus 1. Just by definition, it's a square submatrix. It's non-singular. M is totally unimodular. And the determinant of AI is an integer. Why? Because B is an integral vector. So I'm just taking the determinant of a matrix that has all integer entries. So what I'm doing is I'm taking an integer and I'm dividing it by plus or minus 1. So xi is an integer. Okay, bring that all back to the beginning. We've just proven that for any basic feasible solution, every single entry is either 0 or a different integer. And so if that's true of every single basic feasible point, then the optimal solution is also going to be integral. Okay.
Isn't there, I'm trying to think if there are there any special cases where B is not totally integer? You have sort of a determinant AI that is integer.
I was just thinking about that now because it's something that I didn't think about while I was doing the talk. So off the top of my head, I don't have an example of why that would happen or a proof why that couldn't happen.
I'm trying. I thought of a 2x2 main. I think it could.
I wouldn't be surprised if it could. For some cases, you could find some vector B that might not have integer solutions, but still something works out so that this always is an integer, but I don't know. Generally, just to be safe, we'll want B to be all integer valued. Okay, let me let me throw my corollary down right here, and then we'll get on to the applications to graph theory. Again, I'm going to say that M is totally unimodular. I'm not going to say now that it has to have more columns than rows. I have the same facts about B and C. Then again, the optimal solution to this linear program, and I'm minimizing C transpose X, subject to, now I'm going to use inequality constraints, and I'm not forcing M to be full row rank. This also, so the integral optimal solution is also integral, and this is assuming that it exists. So if this is bounded, if this is feasible, if an integral, if an optimal solution exists, then I can get an integral optimal solution. I'm not going to go through the proof of this. Basically, it just amounts to adding slack variables. Okay, so if you've done any of this before, which I know several of us have done it together in the same class, if you add the slack variables, essentially you turn this matrix into that matrix. And remember, this is totally unimodular by the first thing that we proved. Okay, that's all I'll say about it. We're not going to go into the details of it, but just to say, you can take a whole bunch of other linear programs and put it back in the form that we're interested in using. Okay. So that was the theorem. That was properties about total unimodular matrices. Let's go ahead and go into the world of graph theory. We're going to prove that a couple special graphs or matrices associated with graphs that you've probably worked with before are totally unimodular, and then we're going to use those matrices in graph algorithms that can be characterized as a linear program with a totally unimodular constraint matrix. So another subheading here. Let's take some graph, let's make it directed. Take the incidence matrix of the graph, and what is the incidence matrix? Number of nodes by number of edges is the dimension of the incidence matrix. The incidence matrix is just defined. It's a 0, -1, or 1 matrix, where we say the entry is -1 if node I is the origin of edge j. It's +1 if it's the endpoint. Of edge j, and everything else is zeros. I imagine you've probably worked with these a lot, but I don't know if you noticed that these are always totally unimodular, and that's nifty for a lot of graph algorithms. And we'll prove this, because it's not too complicated to see why this has to be true. Maybe again, just so we've got a visual aid, let's just take a really small, simple graph right here of 3 nodes, and I'm going to say this is 3 edges because one of them is bidirectional. So this is node 1, node 2, node 3. There's my 3 by 3 incidence matrix. So proof. Let's take a submatrix, or start like this. We're going to prove it by induction. So the base case is pretty easy because the base case is just saying if all 1 by 1 square submatrices have determinant 1, 0, or -1, then the base case is done, which is obviously true. All the entries are 1, 0, -1. I'm not going to bother writing that down. Say I assume this holds for all submatrices, all square, up to size k minus 1 by k minus 1. And when I say this holds, I mean the determinant is 1, -1, or 0. And now we're going to prove that if I take a submatrix U, it's k by k, then U is going to have determinant 0, 1, or -1. Okay, we're just going to break this down in a couple different cases. What happens, first of all, if U has a column of all zeros? Of course, its determinant is just 0. So that's kind of a trivial case. Rather than writing down there, let me just go back up here. The next case we're going to do is what happens if the minimum number of non-zeros in a column is 1, and then what happens if every column of U has 2 non-zero entries. Case 2, U has a column with 1 non-zero. This is kind of like, yeah, question.
Does this mean that if you randomly generate a matrix with entries 1, -1, and 0, then it will be totally like unimodular?
No, no. So you can. There are a lot of counterexamples of that. If you take all 1s or -1s, no zeros here, but I could put zeros in it and do something else. If any matrix has this as a submatrix, that does not have determinant 1, 0, or -1. And so there are a lot of cases where the converse doesn't hold. So we do have to be careful of that. Okay. Okay, so here in case 2, we were just saying if U has a column with just 1 non-zero, say take this right here. This is the same type reasoning that we used when we proved that M with an extra vector e sub I tagged onto it is going to have determinant 1, 0, -1. We're doing this thing again where I have a column with only 1 non-zero entry. And so the determinant U is going to be equal to plus or minus the determinant of, just call it U star, where U star is a smaller submatrix. Yes, Kyle.
That's
Put
okay.
up.
So the column you're talking about here is the one you just added to the k minus 1 by k minus 1 matrix, right? It's the k column.
Right, so what I'm saying is I've chosen some U, and somewhere in here I find a column that looks like this. Okay?
I think I understood this wrong.
So this case, so case 1 looks like
No,
this.
I mean the base step. I mean,
Oh, yeah.
when you took U, was the K minus 1 by K minus 1 matrix a submatrix of U? Because there's a.
Now I'm just saying, I'm just assuming that if you give me any old K minus 1 by K minus 1 submatrix, I don't care what it is,
Yeah.
it's going to be of determinant 1, negative 1, or 0.
Okay.
Now you can think of this next step as saying take one of those and tag an extra vector on. You don't have to think of it that way though. I would rather just explain it as saying, okay, with this in mind, bring to me a K by K submatrix. It's going to fall into one of three categories.
Where the K minus 1 by K minus 1 matrix is included in the K by K, no?
It will.
Okay.
I mean, give me any K by K matrix, it will have K minus 1 by K minus 1 submatrices in it, right?
For K greater than 1.
Right. Like they will automatically be in there, one way or the other. So case 1, determinant is equal to 0. This case right here, we're saying I've got just one column. If I write out the determinant based on this column right here, it's this entry times a cofactor plus this entry times a cofactor plus this entry times a cofactor. In other words, it's plus or minus 1 times the determinant of a K minus 1 by K minus 1 submatrix. And so I'm still going to get determinant 1, 0, negative 1. And in the last case, let's write it this way. All columns of U have 2 non-zero entries. And in this case, the determinant has to be equal to 0. Why is that true? Well, let's first just look at our illustration here, and we'll reason through why it's true for any old situation we might find ourselves in. If every column has 2 non-zero entries, one of those non-zero entries is a 1, one of them is a negative 1. So if you take the column sum is going to be 0, right? Whether it's like this tiny thing right here, or a different case where I have a bigger submatrix, but it's still a negative 1 and a positive 1, that just means that the rows are not linearly independent. And again, this is because, or we can see that because the column sum is 0. So if the column sum is 0, rows are not linearly independent, the determinant is 0. So these are the only cases that could happen. So therefore, the proof holds by induction. Okay. Okay. I'm going to squeeze in one last theorem about a matrix, and then we're going to move on to our specific examples of graph algorithms. This one I'm not going to prove just because it's pretty much exactly the same thing here.
Just a quick question.
Yes, question.
So the inductive step was used in case 2 specifically, right?
Right.
Nowhere else.
Right, pretty much.
Q by definition, every column in U has 2 non-zeros, a 1 and a minus 1.
Yes, yes, but when I take my submatrix, it might not have, right? Like if I take this one right here, just 1. Okay. But you're right, this is where I use that induction step. Okay, also, let's say now specifically that G is a bipartite graph. Then the unsigned let's call it B plus. Unsigned incidence matrix, which is just an incidence matrix where I have all positive ones. So if I were to do the unsigned incidence matrix of this, which actually this is a great example because that happens to be bipartite as well, then I'm just putting pluses there for all the ones instead of negatives. Okay. This is also totally unimodular.
Kind of similar question what Varun
Yeah.
had. Is there an example of a matrix that's just 1s and 0s that's not totally unimodular? That one seems tougher to come up with.
Yeah, just 1s and 0s. Well, if you take the unsigned incidence matrix of a non-bipartite graph, that will be not totally unimodular. Okay, so we're taking G to be bipartite, and we're forming its unsigned incidence matrix, and in that case, it's totally unimodular. If this were not bipartite, this would not be totally unimodular, and this actually will show up directly in one of our next examples, because it makes the difference between an algorithm being NP complete and the corresponding algorithm for bipartite graphs being not that hard. Okay. So we're specifically going to look at the maximum matching problem for a bipartite graph. It's not that hard. The maximum matching problem for a general graph is NP complete, and it all hinges on the fact that that's not totally unimodular unless G is bipartite. Okay, we're going to 250, is that right? Okay, so, okay. Well, we should get through at least a couple of these examples. All right, so we're going to move now just to a few examples. As I said before, the nice thing about these theorems and the nice thing about the fact that these matrices that are associated with graphs are totally unimodular, that leads us to be able to take a lot of very standard graph algorithms and characterize them as a linear program with a totally unimodular constraint matrix. And so therefore, the solution you get to your linear program is automatically going to be integral, which is important for the algorithm. So let's start with, what do I want to start with here? Let's just do the shortest path. Okay, so for the shortest path problem, let's say that I've got a directed graph. The idea is I've got some source node, some destination node. I want to find the quickest way to get from S to T. Okay, we can see in this case right here, I could get to S from S to T that way, but the fastest way, if this is unweighted, you can do this for weighted as well, but just for simplicity for right now, let's just say it's unweighted. There's the shortest path right there. How do I set up a linear program in order to do this for me automatically? So let's introduce the variables that we're going to be working with. At the end of my algorithm, what I want to get back is an indicator vector for the edges. So I want some vector x such that x ij is 1 if edge ij is included in the shortest path. If it's not included in the shortest path, I want that to be a 0. Okay. So what I'm going to do for my linear program is I'm going to minimize the sum of all these xij's subject to some constraints which guarantee that what I'm going to get back is a path. So I want constraints to tell me I have a path, and then I'm going to minimize the length of that path. So how would we set up constraints for paths? Well, this is what it amounts to. B is the incidence matrix, and if I multiply that by x, the ith entry of that solution needs to be equal to -1 if I is the node corresponding to my source, +1 if I is t, and 0 for everything else. Let's reason through why this has to be the case. Okay. If you take any path from S to T, notice that I want one and only one edge going out of S. Okay? And remember, for the incidence matrix, I've got a -1 if an edge has origin at a certain node. Okay, so this is -1 right here because I want S to be the origin of one of these edges that I'm choosing in my x vector. Okay, so because I have one going out, this should be a -1. Similarly, T is only one edge going into it. It has to be the endpoint of one and only one edge in my path. So that's a +1, and I want it to be 0 for every other path because every other node along the way has the same number of edges going into it as out of it. I don't ever stop at an intermediate node. I come in and then I go out. That corresponds to a -1 and a +1. And so when I do this multiplication here, I'm going to get 0 for everything that's not I equals S or I equals T. Okay. Now you might think at first, well, what I have to set up is say, take a minimum of this, subject to these constraints, and make sure I have to restrict xij's to be 0 or 1. But the beauty is I don't actually have to explicitly restrict xij's to be 0 or 1. They're automatically going to be 0 or 1, because this corresponds to, let me write it like this. So if S is the first node and T the last node, I can write all this more succinctly. By the way, let E be the ones vector. I'm going to be using E as the ones vector in the next couple examples. I can boil all that down to the linear program of minimizing E transpose times my vector x, subject to B times x equals -1, a bunch of zeros, +1. And then as long as I make sure that I require x to be greater than 0, it's going to be integral, because this is totally unimodular. This is integral. So it has to be integer. And why is it always 0 or 1? Because the fact that it's totally unimodular only would make me sure of the fact that it's going to be an integer, right? But how come it's not 2 or 3 or 4 or 5? Well, that's just because I'm minimizing over all the xij's. So I would never have an xij equal to 2, because I could just as easily have it be 1, which would be better for my objective. Okay, so we're saying that automatically I'm going to get all of my variables to be binary. Okay. So there's one example. Now let's do the same thing for another standard graph algorithm, maximum bipartite matching. So imagine you've all seen this before. I want to find a matching on the edges, which just means I need to select edges so that no two edges touch the same node. So that right there would be matching. That would not be a matching because I've got two edges that are touching the same node. And the common way to set this up as an optimization problem is we're going to maximize, by the way, the xij's pretty much the same thing as they were before. There's an indicator vector for all of the edges, and it's a 1 if edge ij is in the matching. 0 otherwise. So I'm maximizing the sum of all these things. Again, E transpose times x, subject to the constraints. This time we use the unsigned incidence matrix of this bipartite graph. You'd actually, even if it's not bipartite, this is how you could set up the problem for just a general graph. The unsigned incidence matrix multiplied by my vector x has to be less than or equal to 1. Why? The fact that this is less than or equal to 1 is just saying, so every row here is basically telling you take one node. Out of that one node, there has to be at least, at most, one edge incident to it in my matching, or else it'd be a violation of constraints. Okay. So if you took this objective function subject to this constraint and restricted all of these to be binary, this will work as an optimization problem for just a general graph, but that's NP complete, binary integer programming, and we also know that maximum matching is NP complete. But the idea is here, if we're talking about maximum bipartite matching, then this is totally unimodular. And so rather than specifically telling your program, I have to have xij either 1 or 0, you can just replace this by restricting x to be non-negative. And the fact that x is less than or equal to 1 is automatically going to hold true because of this constraint right here. Okay. So this right there automatically implies that you can write it like this. Every xij is going to be less than 1. Okay. So again, just one more example of a standard graph algorithm that can be characterized as a linear program with a totally unimodular constraint matrix. I should also write this as E instead of as 1. Better. Okay. And this also kind of sheds light on the fact, it kind of sheds light on the difference between the maximum matching problem and the maximum bipartite matching problem. And it kind of sheds light on what's going on. How come one of these problems is really hard? How come one of these problems is a lot easier? It's all tied into whether or not this matrix is totally unimodular. And that goes back to your question, Jimmy, of how do I find a matrix that has all 1s and 0s that is not totally unimodular?
Yeah, I figured it out.
Right.
It's because every non-bipartite graph is going to have K3 as an induced subgraph, and then the determinant of K3 is going to be plus or minus 2 up to ordering.
Gotcha. Yeah, so if that's what it amounts to, that's what's going on under the hood. Okay. Yes, question?
What does it mean that vector is less than E?
So this constraint right here, if I were to take let me just go ahead and write out the incidence matrix of this, or at least one column of it right here. Let's say this is node 1 right here, and it's got a 1 right here because of edge 1. It's got a 1 right there because of edge 2. And it's got 0s. It doesn't touch any other edges. And now I'm going to multiply this thing by some vector x. This is x corresponding to the edge from 1 to 2, x corresponding from the edge from 1 to 3, and then some other things here. So what would go wrong if I made both of those two things equal to 1? So if I said this is 1 and then this is 1, I multiply this column vector by this matrix, I get 1 times 1 plus 1 times 1, that would equal 2. And so it'd be a violation of constraints, because what I'd be saying is include both of these two edges in my matching. And so that's why we just have to make sure that this is going to be less than 1.
The entry of, okay.
Right, so choose this one, choose that one, or don't choose anything. Okay. Okay, I think we've got time to wrap up with taking a look at the minimum ST cut, and then we'll be done from there. A lot of times the way people present the minimum ST cut is to present the maximum ST flow, take a dual of it and say there, that's the minimum ST cut. But we're just going to jump right into the minimum ST cut and see how that can be characterized as a linear program with totally unimodular constraints. This one's slightly more involved because I want xi's and wi's. These are going to be a binary indicator vector for all the nodes. This binary indicator vector w for all of the edges. So xi is 1 if node I is included in the set returned, 0 otherwise. And in a second, we'll go back, and I should have started with reminding us what it actually is the minimum ST cut problem, but let me finish writing this up, and then we'll talk about what even we're trying to do with the minimum ST cut problem. So wij is 1 if I cut edge ij. Okay, what's the minimum ST cut problem? Again, I have some source node, some other node. I'm going to say this is a directed graph. What I want to do is find a set of edges that I can cut that will separate the source from the T node, the S node from the T node. And I want to minimize the weight of these edges right here. So I might have some weights Cij are edge weights. And I'm going to minimize Wij times Cij, subject to some constraints. Okay, so the constraint is that I have to find a cut that separates S from T, and I want to minimize the cost of that cut. And so where do these come into play, these xi's? So it's an indicator vector for all of the nodes. And so notice that when I cut these edges, it splits the nodes into two disjoint sets. So we'd be saying that this, if this is x2, then that would be a 1. x3, that would be a 1. x4, this would be a 0. And then xt has to be 0. And xs has to be 1. Okay, so we've got both an x vector and a w vector. And what's the relationship between these two? If I have a node I, edge pointing from I to j, I cut this if and only if this is on the S side and this is on the T side. Okay, so if I start off by saying, here are my xi's and these are my wij's, for now let's just say I'm forcing them to be binary, then xi equals 1, xj equals 0, if and only if wij equals 1. So I'm going to cut this only if this is on the S side, this is on the T side. And if I didn't cut it, I could get from I to j. And all of this corresponds to the constraint. If xi minus xj is less than or equal to wij, then I'm going to recover this, which is kind of the property that I want. So this is the property that I want. I'm saying for now, force these things to be binary. Then this constraint will give me this. Let's just test that really quickly. Well, let's try this direction. If xi is 1, xj equals 0, 1 minus 0, so I'm saying that wij has to be greater than or equal to 1. And if I am saying that I'm restricting wij to be 0 or 1, then of course then wij would have to be equal to 1. Right? Now the other direction, you also have to include the fact that I'm minimizing over all of the edge weights. And so wij, if it can be 0, it will be 0. Okay. All right, let's just sum this up quick with the actual linear program we would need to look at, and then we'll leave it at that, and we can open it to questions if we need to. All of this amounts to, if we minimize the coefficients, so these are the edge weights multiplied by this binary vector, this indicator vector for the edges, subject to this constraint right here, turns into this set of constraints. Okay, the incidence matrix comes from this plus xi minus xj, and then if you moved the wij to the other side and say that xi minus xj minus wij is less than or equal to 0, and you put all of those constraints together, this is the form it takes. I know this is being slightly hand-wavy here at the end, but if you just believe me, if we can take this constraint, all of the constraints of that form can be mashed into these inequalities right here. And then as long as we make sure that w is greater than 0 and x is between 0 and 1, then I will automatically get the xij and no xi and wij will be binary. Okay. And rather than writing this as x less than or equal to e right here, we could have just as easily said, put an identity matrix right there, the 0 right there, and say that this matrix, which is totally unimodular, times my vector of the things that I'm solving for is less than or equal to 0, This would be E. So I know that was getting kind of hand wavy at the end and getting a little bit more lost in what all of these different things mean. But again, what this all does still amount to is that I have the standard graph algorithm, the minimum ST cut problem. And if we look into it, I can characterize this as just a standard linear program. I've got a total unimodular matrix, integral constraints right here, and non-negative vectors x and w. And I will automatically get binary vectors. Okay. So that's it.